Hi, this is Chapter 2 of the Single Loop Control Methods course. In this chapter, we're going to be covering control terminology. If you don't get it in this chapter, that's okay. We'll be covering it as we go through the remainder. But just as an overview of some of the terms, local, remote, auto, manual, cascade, we're going to cover those and try to relate what is a control loop, what is the inputs and what are the outputs. It can be kind of confusing. So this particular one will just be a very short talk on terminology to try to set the stage for the remainder of the course. Process inputs. There's really three things that you have to think about when you're dealing with a controller. We have the inputs to the controller, which happen to be the measured value or the process variable. Sometimes you'll talk about MV, and depending on who you talk about, MV could be millivolts, but we're talking about a measured value, or process variable, PV. Sometimes they'll call it Y. So it's a measurement indication. And we have a set point, which is a reference or a desired input. So typically your set point is where you as an operator want the process to be. Your process measurement is where you actually are. The controller's job is to calculate the difference between what you want and where you are and come up with what's called an error. The error is just the difference. That error is then acted upon by the controller to convert that error. Think of it like a teeter-totter. On the one side is you have your error. The other side, you have your action. Your action can be a change in the valve, it can be a change in a drive, it can be a change in, well, in general, we call it a final control element. It can be any of those things, anything that has an impact on your process. If you're driving a car and you turn your steering wheel and the wheels don't turn, you don't speed up, you stop because the actuator is broken. The action is linked to your actuation. Your measurement are your instruments, your set point is your operator reference, and your error is done as part of the calculation process. Where does tuning happen? Tuning happens between the error and taking action. In terms of that teeter-totter, where's the fulcrum at? If it's a little error, do I get a big output? Or if I have a big error, little output? Where's that fulcrum fall? That's what we're going to call. These are just the introduction to the terms that we're going to be using. This is an old picture. It came from a book from a long time ago that I still like. It shows our manipulated variables. The manipulated variable is that final control element, and it's not on this chart, but just sort of remember FCE, final control element. That can be an actuator, it can be a drive, it can be a motor, it can be a throttle, anything a steering wheel that causes something to move. So it's a manipulated variable. Your process it can be the temperature of the room, it could be the flow through a pipe, it could be oil, whatever. It's a measurement of a process. So then you have a controlled quantity. What are you trying to control? What do you want the attributes of that process to be at? Those are your control quantities. Your sensed variables are typically your controlled quantities that you want to feed into a feedback controller. The feedback controller, again, it's feedback. Notice it's feedback. So your measurement is fed back into a controller. The controller then does the error calculation based upon the inputs from the set point, which is where you want to be, and where you are. So this is where you want to be, your set point. Where you are is your sensed variable, and then your feedback controller determines what output or what action needs to happen on the manipulated variable to drive your process into your set point. There's two main jobs of a controller. One is if you change this set point, you want the action to happen that will get your process up to the set point. The other one, and this picture doesn't show it, but there's actually more arrows that come into the process. We call those disturbances. If I have a disturbance and my measurement goes away, I want control to bring it back. So set point regulation and disturbance regulation. There are two different classes, and we'll talk about those as we move forward. Set point regulation and disturbance regulation. But this picture really paints the story, and it's called feedback control for a reason. The error has to happen first before the control action can take place. When we get on the other side of that, where we're trying to predict what will an disturbance cause, that's called feed-forward control. Feed-forward is where we're trying to predict into the future based on a known disturbance. We will talk about that in later chapters. If the feedback module is what covers, again, 90 to 95% of all industrial controllers. So let's get this one right before we go into feed-forward and cascade. An example, most of us have driven a car. So when you're in the car as an operator, you have a speed limit typically that is set by the sign on the road. And then you look at the speed of your automobile. If they're different, if it's low, you'll push down on the accelerator and you come up. If you don't want to go too far because you could get a speeding ticket, and your police officer doesn't want to hear you say, well, I was getting close, I was getting there. You want it to get to the set point. So in our terminology here, our inputs would be the desired speed, which is hopefully the speed limit, the actual speed, which is your speedometer. You look at the comparison, and then you decide if I want to put my foot down to add more fuel, remain the same, or less fuel. You're doing that as an operator. Now, some cars, a lot of cars, have a cruise control where this happens automatically. When you hit resume or you hit set, it does this for you. Based on the speeds that you're at, it regulates to that. Now my question is on this little car here, is the only thing that impacts the speed of the vehicle your foot on the accelerator? Think about that for just a second as we further diagnose this. Based on our original picture, our process is our car, the engine car turning the wheels. Our manipulated variable, in this case, we can change the fuel flow. The speed is our speedometer. We are sensing the actual speed. That's what we're trying to control. We're not trying to control emissions. Now the more fancy cars do, but for now, if you're trying to control the speed, you want the speed to match your desired speed, which is the speed limit. So you are acting as the desired set point. Your car is giving you the measurement, and then you take action to regulate. And this goes on and on and on. This is called a control execution. It just happens. For you, it's all the time. Now, in industrial plants, you can still have an operator make those changes, and I'll show you that. But what we're doing here is moving in the phase of putting in these controllers. These controllers are dealing with process disturbances and control set points. A controller typically will have, this is called a faceplate. There's different types of faceplates that will show the measured value, it'll show the set point, and it'll show the output. And so you can have the different tuning parameters, but this is a faceplate. In today's technology, it can be as small as a pixel on a screen, or it can cover a quartered-in controller that you might see at a plant. When a disturbance comes in, a disturbance or a load change is something that affects the measured value other than the actuation or the manipulated variable. So in that car example, if you've been thinking about that, what else affects the speed of the car beside your foot? That's called a disturbance. We have to be able to compensate for that. And that's where I'm showing you here disturbances are coming into the picture. We already talked about your desired speed, your measurement, your corrective action, your manipulated variable. This feedback loop has to happen. And if there were no disturbances, if the road was flat, there was no wind, there was no hills, and the fuel flow and your carburetor were right, you could set it and forget it. That's not typically the case. So this poor guy in the car, what else affects it? Well, I mentioned a few of those. Hills, wind, fuel quality, the weight, cargo, weather conditions. Those are all things that are disturbances that impact the speed of the vehicle other than your foot on the accelerator. Those are called disturbances. Those are called load changes. Those are what cause your control to be a regulatory feedback loop. We are measuring the process. When something happens other than a manipulated variable, that's a disturbance. We adjust the manipulated variable to get us back on target. That happens 24 hours a day, 7 days a week, well, every second this is going on. In the industrial world, if you can imagine a heat exchanger where you've got this process coming through, and this guy is feeling, this is our input and this is our output. So I don't recommend that you go grab onto a pipe. You may lose your hand. But if you, in this picture here, he's measuring the temperature, and here he is manipulating the control or the actuation device to change the flow of coolant through that particular heat exchanger. So if he opens it more, it'll take more heat out and less. So he has a control network. So he can realize there's an input and an output relationship. If he changes the actuation device, he can feel it. That's a control network. That can be done in hand. But if you're an operator doing it, you're very limited to how frequently this action can be taken place. That's why we put in controllers. Again, this is from an old book where you put in some sort of a thermocouple through a transducer, you run it into your controller, it takes the set point and measurement and converts it into an action, which would maybe be a single-seated globe valve, and then this is the control actuation. These are still very common. They're everywhere. Now this middle layer may be replaced with a control network where you have hundreds of these. But this continuation of regulation is what goes on. And they work great unless this controller gets out of calibration. What happens if you think you're going the speed but you're off by 10 miles an hour? You still get a speeding ticket. Same thing happens in the industrial world. If the control isn't calibrated right, it can think it's doing the right thing and be causing you problems. There has to be a regular maintenance action put on these control loops. Now, in the control world, you hear the terms manual and automatic. Manual is when the control is operated literally by an operator. Automatic is when you flip the switch to automatic and then the control starts to run on its own. That's manual or auto mode of the controller. Typically, this is what you try to do is you get your process, which I'm showing you back here, a process. How do I get that process into what's called a block diagram? A block diagram is a way of relating the input and the output of each of those components. So here I've got a process, I've got a sensor, I've got a transducer, I've got a controller, I've got an actuator. So each one has an input and an output. In terms of a block diagram, it might look like this. Anywhere you can start, and this is what you can see more clearly, what we call a feedback loop. Notice it's a loop. It's a control loop, where we have a controller that has a reference set by you, or your operator, or your production, and then you output to typically a transducer that converts that current to a pressure. In some cases, it goes directly to a smart actuation device. That actuation device affects the process. The process then goes through some sort of a transducer. This happens to be an orifice place, but it could be a mag flow meter, it could be a Venturi. There's a bunch of different types of instruments that you could plug in here for measurement of the process. Then you convert that back to something that the controller understands. Any one of these, and then later in the book we'll talk about nonlinearities, things that can cause your control to break. Any one of these. It's not just tuning. When I get called in, so I got a tuning problem, this is what I have to go. I do visual inspections of the process, of the actuation, of the instrumentation, the transducers. I do bump tests on the process before I ever get to tuning, and that's what we're going to talk about. Controllers can come in a wide assortment of shapes and sizes. We can get into, these are just two, but there's literally hundreds of different types of controllers. Whether they're physically mounted on a wall or they're an icon on your control system, it really doesn't matter. Those functions that we just talked about are still present. This is a picture that we tried to put together that really illustrates what we're talking about. When we say do a manual bump test, we'll talk about that. But what we're talking about here is typically you may have push buttons or you may enter a 0 to 100%. But what happens is through manual or hand, sometimes they'll say in hand or local mode, I inject energy and I go directly to the output. And so it's like I'm down at the actuator changing it. That's a manual operation. If I'm in an automatic mode, it could be the same two buttons, but now they're mapped into the control network. And so my controller uses those as a set point. It compares that to the measurement and converts that into an error, and then the error is converted into an actuation change. So just when we talk about auto or manual, we talk about open loop and closed loop. That's what we're talking about. Closed loop, we are running through, well, actually if you look at this picture here, closed loop, you're actually touching every one of these parameters. Open loop, you're typically taking the controller out of the equation. It means that you're making a change and then you make the decision on what the next change should be. That's called an open loop. Closed loop, the controller is deciding what the next change should be. Again, we're going to talk about open and closed loop and auto and manual, but I'm just introducing those terms now. You also hear about local remote, auto, manual, local, remote. Typically, when you're talking about local and remote, you're talking about two controllers that are actually talking to each other. A good example is a tank. In this case, we have an inlet flow and we have an outlet flow. And it's actually the difference between these flows that govern this level. If there's a difference, it'll increase or decrease. This outer loop control is only interested in the level, and it makes a decision on what the inner loop should be. The inner loop, it doesn't care about the level. It just cares about this flow. It just cares about this flow. So this inner loop worries about the flow. The outer loop worries about the level. So that's called a cascade control algorithm, where there's an inner loop and there's an outer loop. And the handshaking between those two is what's called local remote. If we're in local mode, that means that you're making changes on the inside here. If you're in remote mode, that means this out guy is talking. And we'll talk more about that. But just so that there's feedback, this is a feedback loop, but so is this. But this feedback loop, part of its what is the actuator? That's a good question. On the inner loop, what's the actuator? Well, it's the valve to the flow. For the tank level, what's the actuator? Literally, it's this whole box. It only moves when the outer loop asks for it. So we're going to talk about that because you have different tuning techniques for each of those. Another term that you hear about is bumpless transfer or non-bumpless transfer. It's kind of backwards in how it's defined, but it has to do with set point tracking. In other words, if you turn the control off, what happens to the set point when control flips from auto to manual? In this case, on the top, the set point stays constant. And let's say a disturbance happened, so the measurement slid down. Okay? So now, when they turn control back on, there's a difference. So you start moving, you have an error. As soon as you have an error, the presence of an error, you're going to get a change. So in the top one, you actually move the actuator, yet they call that non-bumpless. That's why this is confusing, but it has to do with what we're doing with the controller. On the bottom one, you can see as soon as they flipped it to manual, the set point and measured value started tracking. So the difference is 0. So when the control was turned on, there was no change in the actuation device. That's called a bumpless transfer. You didn't bump the process. Here we're talking non-bumpless, which means we bumped. It's a double negative. So in the top one, and in each control application, you have to decide, what do I want to do when I come back from manual mode? Do I want to be where I was, or do I want to regulate? Typically, we'll get into the rules as we move forward. I'm just trying to define set point tracking, auto, manual, local, remote, bumpless, non-bumpless, and we'll go through that. This just gives you another idea. There's still some pneumatic devices out of there. There's still some 3 to 15 PSI. There's still 0 to 100%. Typically, it's just a scale. So 0 to 100% as far as an output's concerned. 50%, I may be able to, if you had a current loop reading it, you'd be at 12 milliamps or 9 PSI if it's 3 to 15. Each one of these transformations is a transducer, and those transducers, depending on what vintage, I've seen those go bad. So it's not tuning at all. It could be the transducer device. Another thing I just want to touch briefly on is reverse and direct acting. That can be confusing. Reverse and direct acting has to do with the direction the actuation device has to go as depending upon the error. For your example, if your car, if you notice that you're off the road and you want to get back on, you're going to move your steering wheel in the direction that you need to go. Well, in some devices that are called reverse acting, you have to can you imagine being on the left side of the road and turning your wheel to the left to move back? That's called reverse acting. There are processes like that have what's called a negative process gain, where I increase and the process goes down. Those happen, and sometimes they're hard to see. But you have to know when you set up your controller, when I have an error, do I open the valve or do I close the valve based upon that error? What's interesting about this is if you get it wrong, you know very, very fast. I've had cases where I didn't, and each vendor unfortunately defines reverse and direct acting just a little bit different. So typically I recommend that you go down to the manual and look, and a lot of times they'll have arrows that show if it, but if you get it wrong, it exponentially goes unstable. So you'll know very, very fast if you get the reverse acting and direct acting flag incorrect. There are different types of transmitters that take your here's a picture of our control loop. So we have our set point, our controller, our final control element, our process, our disturbance comes in. We measure that through a sensing device. That sensing device gets fed into a transducer that can convert that back. So here's our control loop. But it can also go to recorders, indicators, alarms, interlocks. There's a whole series of places. That's why there's a lot of time spent on sensors, sensor precision, sensor maintenance, sensor correlation, calibration, all that stuff. But keep in mind, that can be fed back into a controller. So if your calibration's off, your control will control the output to move the measurement in the direction of the set point. That's why all of the calibration is important. So we just covered a lot of terms, and some of these may be new to you, some of them you may have heard before. each vendor covers those terms and can be a little bit different. So I recommend that you look at the vendor description, the control loop that you're about to go to. But in general, you'll hear about local and remote, auto and manual. You'll hear about current loops, PSI outputs. You'll hear about disturbances, open loop, closed loop, auto, manual, cascade, inner and outer. Those are some of the most fundamental terms, and that's what we covered in this section. This will be a great platform for the remaining sessions. The next session up is we'll get into process identification.